All right, hello everyone. It's 9 p.m. in Melbourne. It means it's time to start this session on data quality and preparation. We have three wonderful papers lined up to be presented by three wonderful speakers. So we will have three talks. Each talk will be for 15 minutes, and we will have 5 minutes for questions and answers session. The first paper is entitled Collaborative and Interactive Detection and Repair of Activity Labels in Process Event Logs. This is a paper by Sarah Sadanlikina-Nassel, Arthur Ter Hofstede, Suryadi, and Selen Turkai. So Sarah will present the paper. Sarah, please. Proceed.
All right. Thank you, Artem. Hello, everyone. I'm Sarah Saderian-As, a PhD student at the School of Information Systems at Queensland University of Technology in Brisbane, Australia. On behalf of all co-authors, Professor Arthur Ter Hofstede, Dr. Suryadi, and Dr. Selen Turkai, I would like to present our paper on improving the quality of activity labels in process event logs. Among the key elements of process event logs are activity labels, which represent the tasks that have been performed, such as admission, medical assign, inward, etc. One of the issues that have been observed with real-life activity labels is that some of them have the same meaning but different syntax. And these labels are the focus of our paper. Consider an event log coming from two different systems. System 1 records the action of a patient being visited by a doctor as medical assign, while System 2 records the same action as doctor seen. If we just naively take these two activities as different, the discovered process model will look like this, where medical assign and doctor seen are considered as two alternatives, although they are actually the same tasks. It can also cause problems for performance analysis, where the answer to the question, what is the average time doctors spend on consulting patients, would be different, depending on which activity to consider as a consultation. Also in conformance checking, we will see medical assign in the prescriptive model, and all doctor seen activities will be treated as a deviation. Due to the importance of activity label quality issues and the problems they may cause for the analysis, they have been studied in the process mining literature. A number of computational approaches have been proposed at event log or process model level, which use some similarity measures to identify activity matches. But the problem is that dealing with activity labels is really context dependent and requires domain knowledge. And this has been the motivation for human-based approaches. However, most of the human-based approaches try to identify activities with the same meaning and different syntax. But in our approach, we not only detect, but repair those kinds of activities. We propose to use crowdsourcing along with gamification techniques to detect and repair activities with the same meaning and different syntax. Crowdsourcing provides a diversity of knowledge and skills of a large group of people through an open call, without any restrictions to their physical location. Gamification is the use of game elements in non-gaming systems to improve user engagement. It has been applied and is growing in popularity in many domains, but has received limited attention in process mining. We use gamification to increase user engagement, which leads to providing better advices for quality improvement. In order to increase user engagement, and based on the Octalysis framework for gamification design, our approach follows a number of motivational drives. Development and accomplishment is the internal drive of most people for overcoming challenges, gaining knowledge, making progress, and achieving goals and mastery. In our approach, we implement collectible points, levels, badges, and progress bars to set goals for the players and inspire their feelings of achievement. Epic meaning and calling is in play when people assume that they are doing something bigger than themselves, such as saving the world. In our approach, we regularly narrate real disasters that had happened due to poor data quality, and this gives the players some context about why they should engage in the game and how they can potentially prevent similar disasters in the future. Social influence and relatedness motivates people to follow a social norm, like what everyone else is doing. In our approach, we motivate people by reporting the number and the views of other players who have tried the game challenges so far, so that they feel that they are not the only ones who are playing the game. This is the conceptual framework of our approach, which takes an event log as the input and generates a repaired event log as the output, which is of higher quality. This log can be improved even further if it serves as the input for another round of data cleaning through the gamified system. Our approach collects knowledge of multiple domain experts as a form of crowdsourcing, and the gamified system consists of three phases: a pre-game phase where we generate questions from an input log, a gameplay phase where the players interact with the system to suggest quality improvements, and a post-game phase where we repair the log using players' answers. In the pre-game phase, we generate a set of multiple choice questions, each asking players to select all options in the form of activities that are similar to a given main activity. For generating each of n questions, we first find the main act, which is the activity with more similar activities in the log. And then to generate the options, we look for activities similar to main act and activities different from the main act. This is the actual algorithm which has a polynomial time complexity. The game is designed around a number of challenges. A baseline each challenge consists of three parts. A baseline assessment part, which is a yes-no question asking players whether two terms are synonyms or not. These terms are coming from a vocabulary knowledge base, which is a set of true synonyms and different words in a domain. This part is used to assess the level of domain knowledge of the player. The second part of a challenge is a detection part, which is a multiple choice question from our question bank, asking players to select all options that are similar to a given main activity. There are a number of helps provided for the players, such as the frequencies of each label in the log and the number of players who have selected each of these options before. And the last part of each challenge is a repair part, where we ask players to suggest a replacement for the synonyms they have detected. The players can either select one of the synonyms as a replacement, or they can suggest a new label through the input field. The players earn a number of stars and diamonds for each challenge. The stars represent the user experience and are computed based on the number of completed parts of a challenge. And the diamonds represent the player's knowledge and are computed based on the baseline assessment part and the repair part. We skip the detection part here because we do not have the corresponding ground truth. In the post-game phase, we repair the log using players' answers. The idea is to select answers of higher weights, where the weight of an answer is determined by the player's knowledge level, associated with the number of diamonds they've earned in the game. So we repeatedly find a repair with maximum weight for any activity and add this repair to the output. And then we make sure that all similar activities are repaired to the same label and all different activities are repaired to different labels. And this is the actual algorithm which has a polynomial time complexity. We have implemented our approach as a Java web application deployed on a Tomcat server. We selected the BPI 2019 log, and picked 8 labels from the total of 42 labels in that log. And for each of those 8 labels, we renamed 20 to 50% of their instances into a new name with the same meaning. So this resulted in 8 groups of imperfect labels, such as in each group, uh, all labels have the same meaning but different names. For example, this group, clear invoice, CLR invoice, remove invoice, and etc. A total of 27 participants played the game in a 3-week time frame, out of which 21 completed the whole game. This table compares the injected and repaired logs. The injected log had 67 activity labels, which was reduced to 46 in the repaired log through our approach. You can see that the repaired log is much closer to the ground truth, which is the original BPI 19 log, compared to the injected log. And this chart shows the number of distinct activity labels in each of the 8 groups of imperfect labels in the original, injected, and repaired logs. We had originally 1 label in each group, and this was increased to 3 to 5 labels as a result of injection. Through our approach, we've been able to reduce this number to 1 in most groups, except for groups 4, 5, and 7. And this is because some of the repairs that were suggested did not get the minimum weight required to be approved by our repair algorithm. And this can be resolved by increasing the number of players or decreasing a threshold. At the end of the game, in order to assess user engagement, we asked players to fill out a survey. The survey had 8 questions, and each question asked about a desirable feature of a game as per the game flow evaluation framework. The features include the clarity of game goals, the usefulness of the feedback given to the player, the ease of use of the game, the usefulness of knowing crowd views, and the rest. And this chart summarizes the scores for each of those questions. You can see that the maximum score is 4.62 for question number 3, which is the ease of use. And the minimum score is 2.66 for question number 4, which is the usefulness of knowing crowd views. We've observed that some players did not know how to use crowd views because they've skipped the initial demo, which teaches them how to do so. And this might be the reason for this score. The score for other questions ranges between 3.5 to 4, such as 4 for question number 6, which is the overall engagement of the game. And this confirms that gamification is a promising technique for improving user engagement. So we presented an approach for detecting and repairing activity labels with the same meaning but different syntax and event logs. We've used human knowledge or domain expert knowledge through crowdsourcing and gamification techniques. Our approach, the results suggest that we are able to improve the quality of activity labels in event logs, and most players found the approach engaging as a result of using gamification techniques. Some possible future works are evaluating the approach with real imperfect labels, or using some additional motivation drive in the game design, or addressing some other types of data quality issues in event logs, such as timestamp quality issues with similar techniques. Yep. Thank you for your attention. And I would like to especially thank all co-authors for their collaboration, and thanks to Professor Movin for her contributions. Thank you.
Thank you, Sarah. Thank you for this wonderful talk. Let's move to the questions and answers session. If you have questions, you can type them in the Q&A function of Zoom, or raise your hand and I will unmute you. Raise your blue hand. There's a question from Will van der Rast. I will allow to talk. Yes, please.
Can you hear me? It's always a surprise with the system.
Very good, very good.
Okay, very good. Yeah, so thanks for the presentation. I think the gaming part and the setup was very clear. What was unclear for me would be also at the end you talk about timestamps, but what was unclear for me is what would be, let's say, process mining or event log specific. What I mean by that is that for some of these problems, I don't know, you can look at the activities before and after and get a hunch of what it could be. So I'm interested in the things that you were using that were specific for event log data.
So we were actually looking at activity labels, right? And in the game, sorry, and in the game, as I said, we suggest some help options when the players want to answer question or select the options that are synonyms to a given main act. So one of the help options that we provide is the similarity metrics. So for each option, we just compute a measure, which is the context similarity of that label to the main activity, such as the resource similarity, the data similarity, the control flow similarity, and the time similarity. So that's one part. And also in the pregame phase, when we want to generate our questions, so we try to pick labels that are candidates, are imperfect labels. We don't show all labels in the log to the players. We first try to guess based on like those context similarity measures. We try to guess which activities are possibly imperfect. And then to make sure, we ask players to confirm that or just say, no, they are not imperfect.
Yeah.
So does that answer your question?
Yeah, sure. Because for me, it was not so clear that you were like I can understand like the label similarity itself, like the textual distance and other attributes. But what was not so clear based on your talk was that you were also using control flow similarity.
Yeah.
So if you see an unrecognized activity happening at a position where you often see a particular different activity, you would suggest that activity as a recommendation, right?
Yes. Actually, this paper is mainly based on our previous work, and in that work we try to define some measures, some context similarity measures for activities. And activities that are highly context similar are suggested as imperfect, such as activities that have high control flow similarity or high resource similarity. We just guess that maybe they are imperfect.
Yeah.
And
okay.
Yeah,
thank you.
No problem.
There is a question from Dirk Falland. I will allow to talk now.
Thank you, Artem.
Please, Dirk.
I'd like to follow up a bit on the questions that Will asked. I like the work a lot. Kind of two questions or maybe pointers to follow up. One of the issues we often have in logs is maybe not necessarily imperfect labels, but also labels where you actually, they're too imprecise, right? So a lab test recorded in a hospital event log may mean very different things depending on when it happens. So I think the approach in itself can be changed to also look at this, right? I mean, it's very generic, but I would find it interesting to also see what has to change in the approach to make that happen, right? So related to context, what prior events or succeeding events or context do you have to consider to make that work? And I think it generally relates to the question of building an ontology for the process, right, from event data. So can you tell me a bit how your approach relates to building an ontology of the process?
So regarding your first question, which was about the labels that have the same name but different meanings, so that's somehow the other way around.
Yeah.
I mean, those labels are called homonymous labels. In this approach, we focused on mainly synonymous labels, and because we try to group activity labels based on their syntax. So if their syntax is exactly the same, in this approach, we consider them as the same. So to change the approach to something that can be used for homonymous labels, we need to go to the event level. So, and we probably need a different approach, because then it's not possible to have multiple options and all more than one options are the same. You know what I mean? I mean,
I
probably
understand.
the
I
game
understand.
design would be different, and also in the preparation phase, the way that we try to detect those labels again would be different. We need to go at event level rather than to activity labels.
Yeah.
And for your second question, sorry, what was the second
It was
question?
about how much is it building an ontology, right? In which sense can you see this as ontology building? How close are you there in what you're doing?
Well, the output of the gameplay phase would be a number of detections and repairs. So detections would be a group of labels that players think that they are synonyms, and a repair would be a suggestion for their replacement, right? So in this approach, we have not looked at ontologies, but I think that if we use those detections as like ontology nodes, we can use, I mean, it will be like an input for an ontology making algorithm or something like this.
Yeah. No, I'm asking. I don't know the answer, so
yeah,
it would be interesting to find
yeah,
out.
that might be a next step. I mean, that's something that will be the output of this approach will be useful for creating an ontology.
Yeah, thank you.
No problem.
Thank you. There are two more questions in the chat, but for the sake of time, we need to proceed. I suggest that the people who ask the questions directly address to the speaker offline. And we move to the second paper. So thank you, Sarah, once again. Thank you very much for this talk. Thank you for questions and answers from the audience. Second paper is entitled An Expert Lens on Data Quality in Process Mining. The authors are Robert Andrews, Fahame Emam Jomeh, Arthur Terhofstede, and Haya Ryers. And Robert will present the paper. So once the screen is shared, Robert, you can proceed with your presentation.
Can you not see Arthur? Is it sharing now?
We can see the screen and we can hear you. Yes.
Excellent. Thank you for handling the introduction and introducing the author team. So I'll jump straight into the paper, An Expert Lens on Data Quality in Process Mining. There's a bit of a Greek theme running through this work. Like Sisyphus, who was doomed to labouring, endlessly rolling boulders uphill, system folk like us spend an inordinate amount of time and effort in every project wrangling the high quality complete data that's provided by our project sponsors into a form that's fit for purpose. Addressing data quality issues is usually tedious, ad hoc, manual and repetitive. The focus is frequently on getting the data to a point where analysis is possible. This usually means focusing on what we refer to as symptoms of data quality, things that are observable in the data itself. Often this is because there's a distance between the analyst and the owner of the data. Privacy, confidentiality, legal considerations mean that it's rare that an analyst gets hands-on access to the information systems where source event data is captured. Often we may not even recognize that a data quality problem exists. The data is not rejected by our process mining tool. The tool produces interpretable output and we go ahead and analyze the output. Questioning Questioning something that looks strange may lead us to see something in the data, but even after we recognize that there is an issue, detecting, quantifying and repairing may not be straightforward. Then we see another issue and around we go again. As in the medical world, symptoms are the manifest expression of some underlying condition. A headache may be treated with paracetamol and the pain goes away. However, a headache may be symptomatic of something like not drinking enough water, or it may be symptomatic of a brain aneurysm. Merely treating the symptom to allow the patient to go about their normal day is not a deep enough investigation of the problem. Similarly, merely creating an event log that's not rejected by the analysis tool does not do justice to the project, a view expressed eloquently by one of our experts, as we see here. We devised the ODIGOS framework, ODIGOS means guide, as a guide to understanding how the observable signs of process execution, this is event logs and event data, which we refer to as semiosis. And semiosis is text to which we can assign a meaning, can be explained in terms of three worlds that make up the process mining context. We have the social world, which includes situational or intra-organizational context factors, and the macro, which are external or legal or legislative, etc. factors. The personal world includes, jumped ahead, sorry. The personal world includes the people aspect of process execution. These would be process participants who are directly involved in process execution, and we consider the intermediary between the owner of the data and the analyst as a data curator who turns recorded event data into logs to be provided to the process analyst as belonging to the personal world. The material world includes all aspects of automated process support. Overall, ODIGOS provides a means to systematically examine the interaction between the worlds to understand every line of the semiotic content. So when we were developing the ODIGOS framework, we, the author team, as experienced process analysts, well understood and were well used to wrangling event data. We all had a light bulb moment when we realized the potential of the ODIGOS framework to explain the source of data quality issues in event logs. And we were excited, and we wanted to see whether other process mining experts would share our excitement. So we engaged in some purposive sampling to select 11 process mining experts from 6 different countries. We considered experts to be people who have demonstrated practical experience across several domains, to have multiple process mining related publications and an expressed interest in data quality. We interviewed the experts online to determine their views on the relevance and usefulness of the individual worlds and of 9 causal paths that we extracted from the framework in explaining event data quality issues. We also sought from them their experiences with process related data quality issues. We coded the interviews inductively using open and axial coding approaches. We then qualitatively and quantitatively analyzed the interviews, and the results are presented in the following slides. So here we will go through the results of our interviews, including examples and quotes from our process mining experts. All our process mining experts agree that the social context has an important role in creating data quality issues. And the social aspects that they identified include the ones that we see on the screen here: organizational culture, task priorities, management style, organizational structure, the difference between, say, a hierarchical versus a matrix organizational structure, performance criteria, and legal requirements. So different aspects of the social world also influence process participants and data curators in the way they execute processes, record event data, and extract event logs. And these actions can cause data quality problems. If we consider organizational culture in terms of both the different levels of commitment to the formal processes and in the use of this same IT system, that is intra-organizational studies, can impact on process participants in the way they carry out processes and record event data. And this can create data quality problems. And we see a quote here from one of our experts talking about two organizations using similar IT systems. The configuration was similar, but they do the processes differently. So that's an example of how organizational culture can result in some data quality issues. And then there was performance criteria. This is like KPIs on process participants, someone carrying out the process. And so performance criteria can impact the way process participants execute processes or the way processes are recorded. The experts provided examples including in a manufacturing context, the process participants' focus was on recording the number of repairs they completed rather than on actually recording their tasks. And we also have task priorities as a factor that can impact on the behavior of our process participants. So here, different contexts require different priorities in terms of completing and recording tasks. So for an example, in an emergency department, the priority, hopefully, is on the patient's welfare. So it's not unusual to see lots of recording of tasks and activities after the fact, after the patient has been treated, or batch recording of activities. The social context can also impact the data curator in the ways that they extract event logs from captured event data. The most frequently mentioned example here was to do with privacy and legal concerns in sharing data. So efforts to anonymize data can lead to issues including missing cases and anonymization in ways that are not compatible with the process mining goals. The social world can also influence the material world, that is the IT systems, specifically in the way that events and tasks are recorded, thereby creating data quality problems. Some examples provided by our experts included performance criteria can impact on the design of IT systems, which can be exploited in fulfilling performance measures in a way that ignores the actual process and the recording of process tasks. Also, if there are different organizational departments that use different terminologies, this could be reflected in the IT systems and in the way that processes and process data are recorded. This could end up in event data using different terminologies, similar to what Sarah just reported with her synonymous labels to refer to semantically similar activities or attributes. The organizational culture can also impact. If there is a siloed culture in the organization, it's likely that there will be different IT systems across the organization that are separated from each other, resulting in siloed data structure. And this can create problems in record linkage from data extracted from the different systems. The material world also has influence on the way event data is recorded and can result in data quality problems through either impacting on the personal world or by directly creating data qualities in event data. We, through our experts, identified different aspects of the material world, including updates to IT systems by the vendor or IT system, for example, a legacy system being replaced by a new system, which has perhaps a new logging approach, change to the processes, new activity labels, and so on. There could be an error in the application architecture. Sometimes an error resulted from the way different applications are connected and can create data quality problems in the event data. There could be differences in the compatibility within the IT systems, and interoperability of different systems can cause data quality issues. So here we will explain the impact of the material world on the personal world in recording event data with 3 illustrative quotes from our experts. So IT systems should support the process. and the process environment otherwise, recorded event data will differ from what actual processes should produce, or there'll be errors caused by process participants in recording processes and activities. The interfaces and the design of the IT system should support the process and the process participants' environment. Otherwise, you will see errors in recording event data. Lastly, the interoperability of IT systems and the data curator's knowledge of the organizational context and expertise in linking data can result in data quality problems in the event data provided to the analyst. So for example, integration problems in event data and the so-called scattered case problem where there's no common case identifier across different systems. This slide captures some of the feedback from the experts on the Odigos framework. In our view, the experts got it. They sort of saw the same thing that we did. And many of them said to us that they had also had a light bulb moment, which was fairly gratifying for us. The experts also made some comments. Here we'll group the comments thematically. Firstly, the experts proposed several new roles for Odigos, including intelligent systems or bots. We feel that these things can be accommodated in the material world. And we talked about process analysts, or the experts raised the issue of process analysts. In our view, they are users of the framework, so we exclude this proposed new role. We do include the role of process designer and in the personal world, but we then also include the formal process definitions embedded in IT systems in the material world. Customers, we already feel that we deal with customers in the process participant role, and then data administrator and chains of data curators when multiple people have hands on the data before it comes to us. We accommodated by slightly changing our view of the data curator role. Another emergent theme centered around the question of what constitutes a data quality issue, what distinguishes correctly recorded but infrequent or aberrant behavior from data quality. In our view, we argue that any data quality symptom is potentially representing some reality and should be investigated. There were some solutions to data quality themes. The experts suggested process-aware information systems and designing systems, which guide the participants, and very importantly, improve communication between the analyst and the data curator to make clear the goals of and requirements of the process mining exercise. Overall, we were gratified to see that the experts perceived Odigos as useful, but that its usefulness would be improved by some methodological support. And this work is already in progress. We've already published some introductory work on this in recent ECAS conference. And we also came to realize that mitigation, that is stopping data quality before it gets to the event log, needs to be handled by understanding both ends of the causal path, both ends of the worlds that are involved in the issue, and consider what's plausible, affordable, best return in a particular context. Sometimes you might have to favor one end, one world over the other. Lastly, in future work, we see that Odigos lends itself to diagnostic and prognostic use. We can, given an event log, look back to reason about the causes of event data quality issues and what can be done to fix them. But importantly, if we understand the process mining context in which we're working and ask the right questions about IT systems and culture and the users and so on, we can anticipate effects on the process mining analysis and take steps to deal with those beforehand. We also look to providing guidance for remediation and prevention based on understanding context strategies. So lastly, to sum up though, we may not be able to solve all data quality issues, but perhaps for systems folk like us, we may not have to push boulders uphill, only along the flat. Thank you very much for your attention. I'm happy to answer any questions.
Thank you, Robert. Questions from the audience? I think we have time for one quick question to move on. If you have a question, you may probably raise your hand, virtual hand, and I will unmute you. Okay, I don't see any questions, so maybe I can ask one question in these circumstances. So this story about fixing symptoms versus fixing the cause, I think this is very interesting. And at this stage, at least as I understood this work, you are classifying quite in depth the symptoms. So what would take to move this work to the next stage where you will start fixing the causes of those symptoms? So how you look into that?
We are, as you said, classifying symptoms, and using the framework, we are looking back here. So when we see symptoms in the event log, we're looking at the ways in which the symptoms came there by following the paths backwards. And we're trying to generalize the sorts of issues that might directly create an issue in the event log, or by working along the arrows, look at root causes. So if we can expand a little bit on the framework to be more general, but capture, we don't want to be too explicit, but be able to at least provide almost a taxonomy of direct causes and root causes. And from that, by understanding the process context, we can then devise prevention and repair activities that are that don't compromise the goals of the process mining analysis.
All right, thank you, Rob. Thank you once again for your talk. I suggest again, for the sake of time, we'll move on. There is one question from the audience, but I recommend that the author of this question contacts the authors of this paper and well, starts the discussion. Okay, the third paper of today of this session is queuing inference for process performance analysis with missing life cycle data. And this is a paper by Guy Berkenstadt, Victor Gall, Arik Shenderovich, Roy Schraga, and Matthias Weidlich. And Roy will present the paper.
Thank you, Artem, for the introduction. So hello, everyone, and thank you for attending my talk. My name is Roy from the Technion, and today I will present our paper, Queuing Inference for Process Performance Analysis with Missing Lifecycle Data. This paper is a product of a joint work with Guy and Avi, which are also from the Technion, Arik from the University of Toronto, and Matthias from Humboldt University of Berlin. This is the outline for my talk, beginning with the motivation for this work, followed by our methodology, results, and concluding remarks. As a way of motivation, consider, for example, the following hospital. In this hospital, patients can go through 3 treatment steps: vitals, consultancy, and imaging. This hospital has a system of queues, which also provides a process that defines that vitals, if conducted, happens before consultancy and imaging. Yet, some patients arrive directly into these treatment steps. And in addition, all these treatment steps are recorded in an event log. The event log contains the start and the completion events for each of the activities, as well as the time that it occurred and the resource that conducted it. For example, the vitals activity has 4 corresponding events in the log. As a final note, there are 2 types of arrivals into the system, namely external and internal. For example, the vitals step can only have external arrivals, while, for example, the imaging step can both have external arrivals and internal arrivals. For the internal arrivals, we assume that the transition times are negligible. For example, once patient number 11 completed the vital step, she directly arrives at the imaging step. Looking into each of these steps, this is our view of a queuing activity lifecycle. Looking at a single activity, we consider three lifecycle states: arrival, start, and completion. The start and completion events are known since the resource who conducted this activity reports them. Yet, the time at which the patient has arrived to the system is usually not recorded. In what follows, when the patients arrive externally, their arrival time is missing. This, in turn, withholds our ability to provide the patient with the queue length and the waiting time. In this work, we focus on predicting process performance indicators with missing life cycle data. Specifically, we're interested in the following questions. What is the queue length in a given timestamp? And what is the waiting time for a customer who enters a queue? These are two very important questions which are crucial for locating bottlenecks and understanding system dynamics. In terms of related work, the first attempt to combine queuing theory and the statistical approach was done by Larson in 1990. He coined the term queuing inference engine for a set of techniques that try to reconstruct performance measures such as queue length and waiting times from data. Larson's approach and those who followed make multiple assumptions regarding the distribution of data. For example, Poisson arrivals. The work by Bert Simas made the approach more efficient in terms of computation, and Mendelbaum and Ziltein propose an extension to the QIE networks for networks of queues. Another related work is done by Mike Jordan and Chris Sutton, who proposed Bayesian inference approach to estimating queuing parameters under missing data. Lastly, in process mining, the approach by Senderovich et al. Reconstructs queues when various information about the log is available. However, they do not handle the case that the arrival into the system is unknown. We move now to our proposed methodology. We begin with some assumptions. First, we assume that the server is always busy. This means that in case there is a patient waiting for service and there is a server available, she immediately starts the service. Second, we assume that there is a one-to-one correspondence between an activity and the resource. Finally, as I stated before, we assume that external arrivals into the system are missing. Now, I will present an overview for our framework. The main input for our framework is an event log. Out of the event log, we generate two sets of features. First, we utilize a queuing inference engine, or QIE, to generate a queue length distribution, out of which we create the first set of features. In addition, we directly use the event log to gather some log-based features. We then combine the feature sets to create our suggested feature representation. This feature set is then used to provide the predictions for the aforementioned process performance indicators, namely the queue length and the waiting time. One of the main components in our feature extractions is the QIE, Queuing Inference Engine. The QIE is a statistical method based on hidden Markov models that provides performance estimation under missing data. In this work, we use a QIE to construct a distribution over the queue length. Using QIE comes with an additional set of assumptions. Specifically, it assumes Poisson arrivals, a first come, first served policy, and non-idling resources. All these assumptions rarely exist in real-world datasets, and theoretical benefits are usually analyzed in sterile scenarios such as MM1 queuing systems. Yet, as we show in our work, using a QIE to generate features to be used in a supervised learning fashion, as we do in this work, is able to provide accurate predictions even when it comes to real-world data. After briefly describing the QIE, we now turn to the feature extraction. Having an input event log, we first use a QIE to generate a queue-length distribution. Since one cannot simply feed a distribution as a feature representation, we offer the following set of features. We divide these features into 3 groups. The first includes features that capture the central tendency of the distribution. Specifically, we use the mean, the median, and the mode of the estimated distribution. Note that the QIE enables us to obtain the exact theoretical queue-length distribution conditioned on the event log under the aforementioned assumptions. Thus, theoretically, the mean may serve as a prediction for the queue length, as the expected value is known to be the best least square predictor of the value itself. Then, aiming to discretize the distribution, we use its quantiles as features. Specifically, in this work, we use deciles. Finally, as we aim to capture the distribution dispersion, we use the moments of the distribution, specifically the second, standard deviation, the third, the skewness, and the fourth, kurtosis. In addition to the QIE-based features, we directly use the log to generate a few process-aware features. In this work, we use the elapsed time, the case number, and when exists, the type of the patient, and the delay between the scheduled appointment time and the actual appointment time. Having the full feature set, we now turn our efforts to the prediction of the queue length and the waiting time. Sorry. Just a second, sorry. We first aim to predict the queue length. To do so, we cast our problem as a regression problem, aiming to find a regressor that predicts the queue length. To implement this regressor, we use an out-of-the-box approach, experimenting with several types of regression models, including linear regression and gradient boosting. Similar to the queue length prediction, we also cast our waiting time prediction as a regression problem. We explored 2 alternatives to learn this regressor. The first uses the predicted queue length as a single feature. Under the relevant queuing assumptions, one can directly express the waiting time as a linear function of the queue length. As a second alternative, we simply use the same feature set as the one that we used to predict the queue length. We now move to the highlights of our empirical evaluation. We used 2 data sets in our experiments. The first data set represents the sterile data simulated based on a MM1 queuing system simulator. The second is based on real-world data coming from a large outpatient hospital in Boston, USA. We begin with the queue length prediction, comparing 3 evaluation measures, namely the root mean squared error, RMSE, mean absolute error, MAE, and absolute relative error, which we term here MARE, over the 2 data sets. First, we see that the gradient boosting outperforms the linear regression, probably due to its ability to capture nonlinear relationships between the features. The MM1 datasets, which represents a sterile setting, for which using the mean of the distribution should suffice to achieve the best prediction for the queue length. While this fact holds for the MAE and MARE, we see that our method provides a slight improvement in RMSE. For the DFCI dataset, The suggested full feature set provides the best prediction. This demonstrates the effectiveness of our approach in real-world scenarios, especially when additional features are available. Similar observations can be seen for the waiting time prediction. Over the MM1 dataset, the baseline provides a slight better RMSE, while the distribution-based features only achieves the best MAE and MARE. For the DFCI dataset, our suggested model provides the best prediction yet again. We now provide an anecdotal analysis looking at one instance in our dataset. The shaded area in the figures represents the distribution. The figure also presents the predictions using the distribution-based features only in red and using the full set of features in blue. For the MM1 dataset, we can see that both models yield similar results. Yet, a different picture is revealed for the real-world data. While the instance remains mainly within the shaded area, we observe a deviation at the beginning of the interval, which is likely due to the violation of the arrival time assumptions. Initially, patients likely arrived in a bulk rather than according to a Poisson process as the QIE assumes. Here, we also see better performance when using the full feature set. The prediction of the waiting time shows a similar pattern. For the MM1 dataset, both models exhibits a similar behavior. For the real-world data, using the full feature sets yields a more agile model that identifies better the changes of the actual waiting times. In particular, a model that uses the distribution-based features only yields higher overestimation in the middle of the interval than the model that uses all the available features. As a final analysis, we look at the most dominant features for each of the datasets and each of the predictors. Overall, as expected, for the MM1, the distribution mean is the most dominant feature for the Q-length prediction. For the waiting time prediction, the distribution dispersion features, and especially the standard deviation, are dominant. For the DFCI, features such as the delay and the elapsed time influence both predictions. The upper quantiles, specifically Q9 and Q8, are also influential, capturing the right tail of the distribution. We now conclude the presentation. In this work, we provided methodology to estimate two important performance indicators, namely waiting time and Q length over incomplete data. We further offer a novel use of the QIE to generate features out of an event log, which can be used for supervised learning. Thank you very much for your attention. And if you have any questions, feel free to ask me or one of the other authors anything. Thank you very much.
Thank you, Roy. Thank you for this wonderful talk. There is a question from Will van der Aalst. Will, I will unmute you. Did it work? No. Yes.
Yeah, it was not really a question. It was more a comment. But I also have a question. So this is related to work that I think you're not aware of Joyce Nakatumba. She did her PhD in Eindhoven and worked on something similar like 10 years ago. So she looked at the effect of workload, like how much work you have in front of you, and then whether you change your working speed. And there's the Jug-Dodson law of arousal, which says that if people have more pressure, they start working faster. And she investigated several data sets, and she often had difficulties with, let's say, incomplete logs where, for example, the start was missing or something like that. So she worked on several heuristics, like I put it in the box, so you can take a look at her thesis. The problem that we had in that study, and that would be my question, is that we had particularly difficulties with things that were, let's say, going over the end of the day. So we have the following problem. Then if information is missing and we are looking, I don't know, at the last activity of the day or the first activity of the next day, that things were very unclear. Did you also experience things like that?
So thank you very much, Will, for the question and for the reference. So I specifically not aware of the work, but I assume that Arik and Matthias are far more aware and know these works. So I will discuss it with them for sure.
So for the record, the technique that you use is completely different, right?
Yeah.
But the problem was in essence exactly the same problem that she addressed.
Great. So thank you for the reference. And actually, we experienced this kind of issues in our event logs. So what we did in this work, we actually trimmed the outliers, the very end outliers of the log. And actually, we once we saw, we assumed that once we saw the last start event, or actually the last completion event, the day was over. So what you refer to, I guess, is places where maybe the some of the assumptions that we use in this work do not hold. And actually, this is one of the main future directions for us. So we stick to most of the assumptions that are mainly used in the queuing theory research. And as we saw, and as you referred to, these are not not specifically hold in real world data. And for now, we just kind of try to treat it similarly. And we hope to do it in future works. And thank you for the note.
Yeah, because you also often see the pattern that, I don't know, resources stopped working at the end of the day, but customers are still submitting new work. And that also creates a bit like you cannot just say, okay, I now don't look at that period, because that period may be very relevant, if you see what I mean.
Yeah, sure. So this
the behavior is simply different at that point in time. And I think that has also impacts if you try to repair event logs.
Yeah, sure. So one final note that in my presentation in our work, I said that we assume that the server is always busy, so there is not kind of an idling server. And this is actually something that happens, and we saw that in our real world data, and we will address it in future works. So thank you.
Thank you.
Thank you. I don't see any other questions coming, so I'll maybe ask a quick question. So how complex can the queuing networks be? Can I compose them arbitrarily, or is it that snippet that you showed on the first slide, or something in between of those two extremes? So how complex can be the queuing network?
So actually, it can be very complex, and one reason that I didn't put all the details on the QIE inference model is that it's far more complicated than a presentation of 15 minutes, where it's not the main idea. So actually, Arik is our expert in queuing, and this is actually something I didn't know before we started working on this project. And in this work, actually, we use it kind of a black box, like an engine just creates for us a distribution. And we didn't go into very much to the inside of the model. But one of the main things that we started looking into is trying to use it in an online fashion. So in this work, we used it in a kind of an offline fashion. We feed the events that we saw in the log into this engine. It gave us the results, and then we use it as features. But actually, there is a different version of this model, which is far more complicated also to implement in real world systems, that tries to do it in an online fashion. And I'll be happy to continue this discussion also with Arik offline if you'd like.
So, but approximately on average size of the queue network you experimented with? I don't know how many servers, how many queues?
I don't have the specific number in front of me, but I can send it. But actually, the graph that I showed.
But is it like dozens or hundreds or thousands, at least in order, or some indication?
No, it's less. The very busy periods include around 50 customer waiting in line, as we see here in this specific instance. The top of the distribution is 35, so it's not. It's per server, so it's not extremely complicated, but it's crowded.
All right. Let's maybe take this discussion offline for later.
Sure.
So, thank you very much, Roy. Thank you for this wonderful presentation. This concludes this session. Thank you, everyone, and enjoy the rest of the day. There are many more interesting talks. There is an industry panel waiting. So enjoy the day. Thank you, everyone, for attending.